Okay, good afternoon, everyone, and let me begin by thanking the organizers for organizing this wonderful meeting and also giving me an opportunity to present the work that we are doing. So today I'll talk about some studies on macro and micromechanical drive that we are studying for athermal amorphous solids. And of course, there are very pretty pictures of different kinds of amorphous solids that we see around us, and we would like to understand how to functionalize these materials, in particular, what are the microscopic processes that are at play and which we can tune and so on. The reason I decided to talk about this is because in the context of the Indo-French meeting, I'll summarize two talks, and both these works are in collaboration with colleagues in France. So the first work is on macro response to this athermal amorphous solids. This is work done by Shumon, who is in the audience, and Kirsten Martens in Grenoble, with whom I have long-standing collaborations, and also some more recent work with Ludovic and Misaki. And then I'll also summarize some results that we have on microscopic forcing, which is what we call active breathing. This is work done by Shantan, who is a graduate student. Magali was a graduate student in Grenoble with Kirsten. So by macro forcing, we mean, so for example, you have some material, we are applying some external macroscopic stresses and so on, so like shear stress and so on, and then you look at the response of the system. And in the context of microscopic forcing, for example, in this cartoon that I have shown here, this could be some self-propulsion and active forcing kind of scenario. And in this context, what I'll also do is I will couple this microscopic forcing with macro forcing and look at the response of the system in that context. So this is a very nice schematic that colleagues have, Alexander Nicholas, Kirsten Martens, and others have gathered together. So you have a whole range of materials, amorphous materials, starting from metallic glasses, polymer glasses, and so on. And then you have this materials which constituent elements are fairly large, like granular solids or emulsions. And this is the regime which is in the athermal regime. And so essentially, in the absence of any drive, nothing is happening to these materials. They're sitting at rest, and only when you apply the mechanical drive, external drive, there is some dynamics in the system and so on. So, and also, the schematic picture of how the response could be is sort of summarized in this kind of schematic plot by Liu and Nagel in 1998, where you have this regime, which is the rigid disordered solid, and this could fluidize either by expanding the system or by some external load or by some finite temperatures and so on. And we would like to understand how this kind of fluidization process happens. And these ideas have now also been extended to active materials. So you have an active solid which is sitting over here, which can be fluidized either via persistence or propulsion or via addition and so on. And in all these contexts, we would like to understand what is happening to the system as it fluidizes or as it freezes and so on. So first, I'll discuss the results on macroscopic drive, which is the response to applied shear stress. So if it's an athermal material, then nothing is happening to the system at rest, and then you apply the stress. So if your stress is, this is some experimental data on some emulsion, and if your stress is very small, then initially there is some plastic flow, and then the system eventually gets arrested, the shear rate goes to 0. And then as we crank up the applied stress, eventually you have some finite shear rate that is emerging into the system, which means there is a steady flow happening inside the system. And then you can gather all this data for the shear rate as a function of stress. And this is how you plot it as a stress versus shear rate. And you have a flow curve for any particular packing fraction, for example. This is data from the same studies. So from here, you go here. So you have stress as a function of shear rate. And then you can plot it as a function of different packing fractions. And you can see that below a certain packing fraction, there is no finite yield stress inside the system. That is, if you go to vanishing shear rates, there is no finite yield threshold. On the contrary, if you crank up the shear stress, then you have this finite yield stress and so on. So essentially, amorphous solids have this, are known as yield stress materials and so on. So rheology in some sense, in this kind of studies, rheology in some sense, it probes the rigidity threshold and also studies the steady flow and so on, and we would like to get some insights from atomistic or particulate models. So we'll look at two different models. One model is a binary Lennard-Jones mixture, so this is quite well studied in the context of glassy systems. And then more recently, there have been a set of studies from Misaki, Ludovic, and co-workers, and Alberto is also part of this work. And so where they have been able to generate glasses which are at very low energy states or more ultra stable, and then one can look at the range of responses depending upon the stability of the glass. So you have a poorly annealed glass to a very well annealed glass, and you can see that the response of the system varies as a function of this annealing history and so on. And so we apply the shear stress to these two different models, and then we see what is the response of this material and so on. So first, for the binary Lennard-Jones mixture, we have different, again here also we have different preparation histories. So what we call, let's say, a poorly annealed state, a mid-annealed state, and a sort of well-annealed state. And what I write here is, so for example, this is since we had earlier discussed about the shear rate, so this is shear rate as a function of time, or the strain as a function of time. And what you can see is that if your stress is below some threshold, then eventually the system gets stuck or the shear rate goes to zero. And if you crank up the stress at some point, the steady flow emerges. And the stress value at which the steady flow emerges depends upon the preparation history. So for a poorly annealed state, it is around, let's say in this model, it is 0.55. And for a mid-annealed state, it is around 0.56. But if you go to really well annealed state, then you see that this number is around 0.83, which is about a factor of 1.5. So this number, which we call the static yield stress or the static threshold, is very different from the dynamic threshold, which one gets from this fitting this kind of a flow curve to a this function to the steady state data and so on. So the simple summary from this is that static threshold depends upon preparation history, and the other thing that one can also do is also look at the fluctuations of this strain. For if you have an ensemble of states, you can look at the fluctuation of this strain and so on, and this strain fluctuations also show some non-monotonic behavior. And from the point of the location of this non-monotonicity, you can characterize a fluidization timescale. And as you can see that this fluidization timescale starts to become longer and longer as you go to smaller and smaller stresses. So we have done this exercise for the other model also, which has a larger stability range. So if you go from initial temperatures of 0.2 to 0.062, and you see exactly the same phenomenology, that basically the yield threshold changes quite a lot from the poorly annealed state to the well annealed state. And in this case, it is about a factor of 3. So here from going from 0.14 to about 0.5 and so 0.442 and so on. So both these models tell us that the static yield threshold depends upon the preparation history of this system and so on. So then to characterize this yielding behavior or the onset of flow, one quantity that people have been looking at is this fluidization timescale, the timescale at which onset of flow happens. And there is a lot of experimental data on this, and more recently, there are different theories which try to predict this fluidization timescale. So there is one study from the group of Benzi using a fluidity model, and they write the fluidization timescale as a function of the distance from the yield threshold, and this is a diverging power law with some exponent 9/4n and so on, where n is this exponent in this flow curve that is there. Similarly, there is a model in which Alberto is also involved, and in this model they predict two exponents, for example. So one exponent is this time scale, or this exponent via which the shear rate vanishes to 0, so t to the power minus nu, and the other exponent is beta, which is related to this Herschel-Berkeley exponent n and so on. And then, so these are two models which have similar kind of flavor but done differently. And then there's also this elastoplastic models, which are like sand pile models with And so there one can put in different kinds of stability history, and there one sees that this exponent actually depends upon the stability of the sample or the preparation history of the sample. So you have two different results. In one case where you have unique exponents which are determined by this exponent n, and in this case the elastoplastic model, it tells us that this exponent can depend upon the preparation history and so on. So we have done this analysis for this soft sphere model, and there we have the time scale for fluidization as a function of stress, and we fit these functions with power laws, and then what one sees is this exponent depends quite a lot on this preparation history, which is not predicted by this two of these theoretical models. The reason being that these exponents are completely determined, in the theory the exponents are completely determined by this Herschel-Berkeley exponent. On the contrary, it has no information about the preparation history of these materials and so on. The other thing that we also try to estimate is this exponent nu, by which the system is going into a frozen state. And we also see that this exponent varies quite a lot depending upon the preparation history. But one has to be careful because we have done other studies in the context of jamming, where we have seen that one really needs to look at very large systems and asymptotic behavior in order to get the correct exponents and so on. Okay. So then the other thing that we try to do is to look at the spatial information about how this onset of flow is happening. So we do what are this some kind of a bifurcation analysis. So essentially what we try to do is we try to find the largest stress at which the system does not flow, and then you add a small amount of stress, and then the system goes into flow. So in this, so this is what we have show here. So this is the non-flowing state, and this is the flowing state. And then you can see that till this point C, which is somewhere around here, the system looks almost identical. And then eventually you see that this bifurcation is happening, that one system goes into flow and the other system continues to remain arrested. So this is almost marginal. And then you add a small amount of stress, which is of the order of 10 to the power minus 3, and then the system goes into flow and so on. And this exercise we have repeated for the other model also, and there we have a better resolution. And there what we see is that for the state which does not go into flow, you see some soft spots that are being generated. But what we determine is that those soft spots are not the relevant soft spots. You need the nucleation of the relevant soft spot in order for the flow to propagate and so on. So essentially telling you that soft spots, the existence of soft spots is, by itself does not guarantee that the flow will happen. You need the nucleation of the relevant soft spots for the flow to be generated and so on. So this exercise we have developed further by, and we use this sort of thought experiment that Misaki had done earlier, so where he had embedded a seed inside the material, which is like a soft zone, really weak zone. And then he had applied some shear to that system, and then he had seen that this soft zone is sort of the source of the shear band that leads to the failure and so on. And we repeat this exercise with the applied stress, and there we see that, so in one case, this case, the system does not go into flow, but if for an infinitesimally extra amount of stress, the system goes into flow, which essentially tells you that even though you have, even if you have a very weak zone sitting inside the system will not flow unless the sufficient amount of stress is applied to the material, or that this plasticity, whatever is being generated here, can emanate outside and try to weaken the system, weaken the zones around it and so on. So I'll summarize this part of the talk. So basically we are proving the response of this athermal amorphous solids to applied macro shear stress. We're looking at the yielding, and we have shown that the exponents depend on the preparation history, the fluidization exponents, and also determined that you need the nucleation of the relevant soft spot for the system to get into flow. So in the next part, I'll summarize the work that we're doing on active breathing and the rheology, which so most of the studies that we listen to on the context of active matter are related to self-propulsion and so on, but there are other sources of activity that is happening inside this different biological systems. One such case is where there are volume fluctuations, and this is an experimental scenario where they have demonstrated that there is a lot of volume fluctuation that is happening inside the cells and so on. And this is another set of data where volume fluctuation is reported in a cellular system and so on. So Elsen-Thiang and Ludovic Berthier, they proposed a model, simple model, by which they tried to incorporate this kind of size fluctuations by saying that the size of these particles have some oscillatory function, and this goes into this harmonic potential, which essentially tells you that the interactions are also as a function of time and so on. And the control parameter is this magnitude of this oscillation, and you need to add some phase factor so that systems are not undergoing oscillation at the same time in the same phase and so on. Otherwise, it will be a pure expansion and contraction. What this showed is that if you increase the amplitude of the oscillation, so this is for very weak oscillations, the system, the system remains arrested, and only if you increase the oscillations beyond a certain threshold, then the system starts to get into large-scale plasticity and flow and so on. And this is the amount of displacement undergone within one cycle of this oscillation, and you see that below a certain threshold there is not much of displacements happening, square displacement, and then it goes into large displacements when it crosses a threshold. This is also seen in the data for mean square displacement, where below a certain threshold you see that the system remains arrested, and if you cross this threshold the system goes into flow. So we are interested to have some, kind of a elastoplastic picture of this sort of yielding scenario that one sees as a function of the breathing amplitude. So we try to identify the local plasticity by looking at the break of contacts between particles or via displacements or via energy change, local energy change. And then we see that all three give us similar kind of signatures, and this is the easiest thing to compute, the number of events that is happening locally. And this is below the yield threshold, and this is above the yield threshold or the amplitude, threshold amplitude. You see there is some local plasticity happening over here, but as you cross the threshold, there is large-scale plasticity that is happening. And this is displacement within one cycle of the oscillation and so on. So we can compute the number of such events that are happening as a function of each cycle, and then we can see that this number of events is some constant below some threshold, and then suddenly it shoots up beyond this yield threshold or the amplitude threshold and so on. And one can also get signatures in the von Mises stress, which is a generalized form, because you have all kinds of stress components that are coming into the picture because of this breathing that is happening inside the system. And we see that the von Mises stress also shows a kink at the threshold at which this large-scale plasticity is happening. So next, what we do is that we impose shear on the system. So this is an alternative way to check for the rigidity threshold of the material. And so we are looking at the steady state of the system. So for different breathing amplitudes, we plot the shear stress as a function of shear rate. So if the amplitude, so this is for zero breathing, so it's just a jammed state. And then as you increase the breathing amplitude, the yield stress or this the asymptotic value of this stress at zero shear rate, it starts decreasing, and at some point the curvature of these functions change, and you have a Newtonian behavior that is emerging at small shear rates and so on, which tells you that the material has fluidized. And this is also seen in the viscosity, which is shear stress divided by shear rate. You have a diverging viscosity at small breathing amplitudes, and at large breathing amplitudes you get a finite viscosity inside the system. So you can compute the yield threshold from this by fitting this function data with the power law function, and then you can plot the yield threshold as a function of the breathing amplitude, and from this you can determine the yield threshold, which almost comes to be very similar to the number that Thiang and Berthier had computed earlier, which tells you that the rheological probe is also giving you the same threshold, rigidity threshold for this material. To come back to to fulfill the circle, so sort of that we also then impose a shear stress on this system, so a certain constant shear stress has some particular value. So let's say it is around 0.015. So if you impose a shear stress at this point, so any material which has a yield threshold below it will yield, and any system which has an yield threshold above it will not flow, and this is what we check. So for example, for stresses, so this applied stress is 0.0015, and for breathing amplitudes 0.04, the yield stress is larger, so the system does not flow, On the contrary, for other systems which have yield stress which is below this imposed stress, the system goes into flow and so on. Or in other words, the imposed stress tests confirm the yield threshold and so on. So then our collaborators, Kirsten and Magali, they have developed a mesoscale model to look at this breathing plus shear. So you have two sources of plasticity. One is this one coming from the external mechanical drive, and the other source of plasticity being the breathing that is happening inside the system and so on. And so both these can contribute to the toppling of this site and so on. And they compute the quantities that we are looking at, number of events, average, the von Mises stress, and then also look at the rheology. And we see that the signatures are very similar, that you have large-scale yielding at some activity, as some threshold activity. Then you have a kink in this von Mises stress. The signature is not exactly the same, but we see a kink around this point. And of course, the rheological behavior is also very similar, telling us that the mesoscale model is doing a good job in describing the physics of the system. So I conclude, so basically we are looking at probing the macro and micro yielding properties of these athermal amorphous solids. And we show that yielding depends on the preparation history. It needs circulation of relevant soft spots. And then we have been looking at this microscale oscillatory active deformation. And we are trying to characterize the elastoplastic fluidization and also the rheological behavior of the system. So thank you for your attention.
A lot of time for questions.
Concerning the part where you look at the time of the failure, the dependence of the preparation. Okay, I understand that the time of the failure is the more interesting part, but did you see the decay T minus nu that so is depending on the preparation?
But this is a little bit tricky because I don't think we have the asymptotic regime, and it could depend upon the system size. So we have numbers, of course. I mean, the number.
No, I mean, if you take a stress which is small.
Yeah, all the stresses are smaller than the yield threshold.
And then you don't see the power law, or you? No.
Yeah. So what you predict is 1.69. I mean, depending on the numbers that we put in and so on.
Yes.
It seems here we are close to 1.69, but I would take that with a grain of salt. I mean.
And it depends on the preparation.
Yeah.
It depends on the preparation.
Yeah.
So, but if it depends on the preparation, then I think we have to discuss.
Yeah. No. Okay, we'll discuss this. Yes.
In the first part of your talk, you showed d gamma by dt. Why does it go to 0 at some points? What is happening in those fluctuations? In the first part of your talk.
Yeah, I mean, so you have the same quantity over here, right? So basically, the system is going into a rest. So there is no further deformation happening inside the system.
I see. And
so your stress is below some yield threshold, that there is no further deformation, the system just gets arrested.
Okay, it's below the yield.
Yeah.
I had a question. So this for the active deformers, I mean, you showed a plot of the transition as for different system sizes, right?
No, so that was data from the previous study.
Oh,
yes.
is it?
Yeah. They had this, yes.
So with increasing system size, it
is a discontinuous kind of.
Yeah, but where does it go? Like the largest system size is.
So this is here, the below the threshold, and then there's this jump.
That's the largest system size, right? So it will converge to some finite age, I guess.
Yeah. That they have shown, yes, they have shown.
Okay. And in the liquid phase, it's like a regular. I mean, because it's active. I mean, what?
So we have to characterize this better, but at the moment it looks like Newtonian fluid over here, but we have to characterize this better.
Okay, if there are no other questions, let's thank.
Yeah, thank you.
Long live India and France friendship.